Welcome, everyone. Today we are starting our look at second-order ordinary differential equations. We will focus on the foundational physics, how we define state variables for computation, and use the simple harmonic oscillator as our primary example. By the end of this session, you will understand why physics naturally leads to these second-order equations. You will be able to identify displacement, velocity, and acceleration in a computational context, and learn the standard procedure for converting one second-order equation into a system of two first-order equations that our Python tools can handle. In physics, second-order ODEs are everywhere because of Newton's second law, which states that force equals mass times acceleration. Since acceleration is the second derivative of position with respect to time, any system where the force depends on position or velocity, like a spring, a pendulum, or an RLC circuit, will be described by a second-order equation. Mathematically, if we define x as displacement, then the first derivative of x is velocity, and the derivative of velocity is acceleration. This means acceleration is the second derivative of displacement. A second-order ODE essentially provides a mathematical rule for determining the acceleration of a system at any given moment. For simple harmonic motion, the acceleration is proportional to the negative displacement, represented here by negative omega squared times x. To solve this, or any second-order system, we require two initial conditions: the starting position and the initial velocity. Without both, we cannot uniquely determine the motion of the object. Most numerical solvers, like the ones in SciPy, are designed to solve first-order equations. To adapt our second-order physics models, we use a standard trick. We define a new variable, v, as the first derivative of x. This allows us to split the original problem into two linked first-order steps. We package these variables together into what we call a state vector, shown here as the list containing x and verses. When we write our derivative function in Python, it must return the derivatives in this exact order: first the velocity, then the acceleration. Maintaining this ordering is vital for the solver to produce correct results. We will be using three core libraries for this work: NumPy for numerical arrays, Matplotlib for visualization, and the solve_IVP function from SciPy's integrate module. In this first block of code, we are setting up our environment and configuring a cache directory for our plots to ensure everything runs smoothly. Continuing our setup, we import the standard libraries and define the default figure size and font settings for our plots. We use solve_IVP specifically because it offers a more modern and explicit syntax for defining time intervals compared to the older ODINT function. Let us apply this to the mass spring oscillator. We start with the physical equation where mass times acceleration equals the restoring force, negative k times x. By dividing by the mass and defining the angular frequency, omega, as the square root of k over m, we arrive at our standard second-order form. Now we perform the conversion to a first-order system. We define the rate of change of displacement as velocity and the rate of change of velocity as the acceleration from our previous equations. This pair of first-order equations is exactly what we need to program our derivative function in Python. Here we define the function show_derivatives. It takes three arguments: the current time, the current state vector, and the angular frequency. Within the function, we unpack the state into displacement and velocity, then calculate the derivatives according to the two first-order equations we just derived. Finally, the function returns these derivatives as a list. Remember that the order here must match our state vector. Since our state was displacement followed by velocity, we return the derivative of displacement followed by the derivative of velocity. Next, we define our physical parameters and initial conditions. We will start with a displacement of 1 meter and an initial velocity of 0. We calculate the expected period based on our omega value of 2 radians per second, which will help us determine how long to run our simulation. We establish our time grid by defining a start time an end time equivalent to 5 full periods, and a high-resolution grid of 1,000 points. This eval array is where we want the solver to report the position and velocity of the oscillator. Running that code confirms our calculation for the expected period. With an omega of 2, we expect one full oscillation approximately every 3.14 seconds. We are now ready to pass all these parameters to the numerical solver. We invoke the solve_IVP function, passing in our derivative function and the time span. We provide the initial state and the specific evaluation times we just created. The additional arguments, like omega, are passed through the args parameter to keep the solver and physics model separate. Once the solver finishes, we check the success attribute and the status message to ensure the integration reached the end of the interval without errors. We also inspect the shape of the solution array, which confirms we have 2 rows, one for displacement and one for velocity, across our 1,000 time points. The output confirms a successful run. The solution object now contains a time array and a matrix of values representing the state of the oscillator at each of those times. We can now move on to visualizing how these quantities evolve. To create our first plot, we extract the time, displacement, and velocity arrays from the solution object. We use matplotlib to plot both displacement and velocity on the same set of axes, adding labels and a grid to make the behavior easy to analyze. Looking at the resulting plot, we see the classic sinusoidal curves of simple harmonic motion. Notice that velocity is 0 when displacement is at its maximum or minimum, and velocity reaches its peak magnitude when the mass crosses the equilibrium point at 0. This behavior makes perfect physical sense. The curves are phase shifted by 90 degrees, or a quarter period. Also, notice that the amplitude of the oscillations remains constant over time. This confirms that our numerical solution is stable and is correctly modeling a system with no energy loss. A more sophisticated way to view this is through a phase space plot. Instead of plotting variables against time, we plot velocity directly against displacement. This part of the code sets up that visualization, using an equal axis scale to preserve the geometric relationship between the variables. The resulting phase space trajectory is a perfect ellipse. For a simple harmonic oscillator, this closed loop indicates that the system is periodic and conservative. Every time the mass returns to a specific position, it possesses the exact same velocity it had during the previous cycle. To be absolutely sure of our results, we can compare them to the known analytic solution for this case. We calculate the exact displacement at every time step using the cosine and sine terms, and then find the absolute difference between this theoretical value and our numerical result. This block of code calculates that absolute error and prepares a plot. We will also print the maximum value of this error to get a quantitative sense of the solver's precision given the tolerances we set earlier. The error plot shows that the discrepancy grows slightly over time, but remains extremely small. Even after several oscillations, the numerical solution is incredibly close to the exact physics, with the vertical axis scale showing that errors are on the order of 10 to the power of -9. The numerical output confirms this high level of accuracy. A maximum error of about 3.8 nanometers for an oscillation with a 1-meter amplitude is excellent, giving us great confidence in using this numerical approach for more complex problems where analytic solutions might not exist. We can also perform a validation check based on the conservation of energy. In an ideal oscillator, the sum of kinetic and potential energy should be constant. We calculate the total energy at each time step using the mass, spring constant, and our numerical results for velocity and position. After calculating the energy, we determine the relative energy change compared to the initial value. We then plot the total energy and the relative change on separate graphs to see if the numerical solver is bleeding or gaining energy over the course of the simulation. The first energy plot appears to show a slight downward trend, but look closely at the vertical axis. The entire variation is happening at the 8th or 9th decimal place. For all practical purposes, the total mechanical energy is being conserved as expected. The relative energy change plot provides even more detail. While there is a tiny drift, it is confined to less than 10 parts per billion. This level of precision is more than sufficient for most physics simulations and confirms that our solver settings are appropriate for this model. Our printed output reinforces this, showing a maximum relative energy change that is effectively negligible. This completes our validation process, showing that our numerical system correctly preserves the fundamental physical laws governing the oscillator. Now it is your turn to explore. In this guided practice section, I would like you to experiment with the model by changing the initial displacement, the initial velocity, and the angular frequency. Observe how these changes affect the amplitude, the period, and the energy of the system. This code block is set up specifically for your experimentation. It reruns the solve_IVP integration with whatever parameters you provide and generates a new plot. Take a moment to think about why the derivative function requires the specific return order of velocity, then acceleration before you run your tests. This final section of the practice code handles the visualization for your custom runs. It plots displacement and velocity over 4 cycles. Use this to verify your intuitive understanding of how changing things like omega impacts the frequency of the waves you see. Here is an example of the output you might see. By increasing the frequency or changing the initial conditions, you can clearly see the resulting shift in the period and the relative scales of x and v. This interactivity is one of the great strengths of using Jupyter Notebooks for physics. In summary, we have seen that solving second-order ODEs numerically is a straightforward process of rewriting them into a first-order system using a state vector. We validated our simple harmonic oscillator model using analytic comparisons and energy checks. In Part 2, we will expand this to include damping and external driving forces.